Well, believe it or not, it's been almost half a year since I bought the mini mill. It certainly doesn't feel like it though. It's been a pretty amazing journey so far, getting to know the mill. I've used it almost daily, made some really cool lathe upgrades and projects, and it's been a lot of fun doing it. Now I know most of you want to know the answer to the question, was it worth it, and would I recommend it? These machines, whilst cheaper than a lot of bigger mills, are still a decent amount of money to buy, and they do have a reputation of having dubious quality at best, so it's not always an easy question to answer. So let me go ahead and try and answer it. So let's start from the beginning. This is my vertical mini mill. It's a Sieg X2.7L, but it's sold under various brands that you might find on eBay or Amazon. The reason that I bought a mill was so that I could produce parts that weren't cylinders. The lathe which I own is very good at producing cylinders and boring holes. Of course you can do basic milling procedures on the lathe, but it's limited by the short cross slide and swing, so you probably won't be doing anything big or complex. And that's why I ended up getting a mill. Having previously bought a Sieg lathe, I knew where to set my expectations in terms of quality and what to expect performance wise. Compared to a proper industrial mill, this is a lot smaller and lighter, but for a hobbyist, it's a decent piece of kit. Size-wise, this mill is about 900mm wide, 620mm deep, and 880mm tall, which is decent for a mini mill. However, mill dimensions aren't exactly straightforward. Because the table moves, it can stick out 600 or 700mm in either direction when the table's fully moved. As a result, it's probably a good idea to have about 1.5 meters of space left free for the mill table to move, plus a little bit extra to spin the hand wheel. Of course though, the work area is much smaller than this. On this mill it's about 500 by 190 by about 340, and that may sound small on paper, but realistically, this is big enough for 95% of all projects I'm planning on doing. And I don't recommend going smaller. On the smaller X2 mills, which are very popular, a very common complaint is running out of travel on the table, which is only about 300mm compared to about 500 here. In my opinion, it's a lot easier to machine oversized work on a lathe than on a mill, so it really does pay to get the biggest table that you can get, hence why I got the 2.7L, which has a 100mm longer table over the standard 2.7. And the work area shrinks further once you add tooling and work holding. For instance, I use an ER32 collet chuck, and that alone robs you about 70mm of space. You can get some of the space back if you use a Morse taper collet, but they're expensive and they aren't really that common. You'll also lose space once you add a vise. You lose about 30mm of space with a small drill press vise, and you'll lose about 60mm of space with a small milling vise. All this is to say is, it really does pay to have a good amount of Z travel. In terms of weight, it weighs in at about 105 kilos for the machine, and about 130 kilos when it's packed in a wooden crate. And that's about double the weight of an X2 mill. Of course, 100 kilos is pretty light for a mill. Even a medium-sized mill can approach 800-900 kilos in weight. Though realistically speaking, this is the largest mill I could fit into this workshop. Just getting the mill to the workshop was no easy feat, and whilst it would be great to have more mass in the machine, I think it does a pretty decent job. And whilst I'm on the subject, be mindful of where you're going to mount it. It should be bolted down to a solid surface, and it should be stable when the machine is in use. For about $150, I was able to make a bench from some 40x40 box section steel, and that was all stick welded together. I made it a little bit taller than most may like it. It's about 1 meter tall, so the table was near chest height. It's a lot more ergonomic to have the work higher up, so I don't have to bend over to look at the workpiece. Before we do a deep dive, let me quickly talk about pricing and other mills that you can choose from. The price does tend to vary from country to country and between suppliers, but in total, I paid about $1,800 Australian, shipping included. Now I was lucky to get this during a sale. Normally the price would be about $2,000 in total, and considering the lack of small mills on the used market here, there really wasn't a huge range for me to choose from. Critically though, this model came with the 1 horsepower brushed DC motor. You can get it with a brushless 1 horsepower motor, but that wasn't in stock when I was buying the mill, and it usually costs an extra $500 over the brushed model. I'd probably recommend the brushless version over the brushed, but I'm very happy with the performance so far. The only time that I've really needed more power from the motor was when I've been drilling large diameter holes in steel. I also briefly considered getting the X2 mill, or one of its many variants. They tend to cost about $1,000, so almost half the price of the 2.7, and they seem to be the most popular model. I'll make several comparisons throughout the video, but to put it simply, it has a smaller table, a less powerful geared spindle, and a tilting column, which really puts me off getting one. And whilst we're on the topic of cost, let's have a look at what you get with the mill. And it really isn't that much. You get some T-nuts, a spindle wrench, a few spanners, and a hex key, although the manual is very useful as it provides very detailed breakdowns of the mill and its sub-assemblies. It does, however, come with a keyed chuck as standard, and it's a decent quality chuck. It's great for drilling with twist drills, not so great with end mills. Though to be honest, maybe 70% of all the work that I've done on the mill has been drill press work, so I get a lot of use from it. You wouldn't want to use end mills with it though. End mill shanks are typically hardened to an extent, and the hardened jaws of the chuck won't grip the end mill. As a demonstration, I built some aluminium, and it's clear that the end mill was pulled down out of the chuck. Optimally, you'd want to use an end mill holder or a collet of some sort. I chose to go with an ER32 collet chuck just because they're so versatile. It's a relatively inexpensive set. I think the whole set cost me about $80. And there's a few other costs you'll need to factor in. Cutting tools, for example, are a lot more expensive than lathe tools. You can buy an end mill set off eBay that will give you about 10 sizes for about $20. I've bought them. The quality is okay. It's a decent set to start off with, but you can be paying $20 plus for a decent end mill. And unlike lathe tooling, they're pretty difficult to resharpen, so it's a very good idea to use a coolant or cutting fluid to extend the tool life as long as possible. WD-40 is a very popular coolant. Other one-time costs will include a vise. I was able to get away with using a low-profile drill press vise for a few months, but it really lacked rigidity, though I was able to produce some really good parts with it. You can spend a few $100s on a vise, but I ultimately settled on a 4-inch import. The total cost for it was about $100, and it's a decent enough vise. You'll also need a set of parallels, and they start at about $70 and up. I also recommend getting a DRO. I'll touch on it later, but these things are a must-have on any manual mill. However, even a budget DRO will set you back about $200. All this is to say is there are some hidden costs to machining, though some of it can be waited on. For instance, I waited a few months before buying the DRO. You can also shop around on the used market depending on how big it is where you live, or you can save money by making your own tools. For example, you can make your own T-nuts. It's quite simple to make a clamp down kit. A fly cutter is a really popular project to do, and if you want, you can make a boring head or a dovetail cutter. The final thing that I'll talk about is the subject of quality, and it really was the area I had the most concerns about. The money that I spent on the mill and the tooling was a very big investment, and the last thing I want are quality issues. Given my experience with the lathe, I had certain expectations from the mill. The lathe was okay out of the box. It turned parts just fine, but ultimately needed a good amount of work to really make good use out of it. And it was a pretty long list of stuff that had to be done. However, I was really surprised at the quality and design and performance of the mill out of the box. It feels like a much more complete and well-designed machine from the factory. As expected, every surface that needs machining is nicely machined. The table is nicely ground, though it will be very interesting to blue it up and test it against a surface plate to see how good the grinding really is. The finish on the dovetails is a huge improvement over the dovetails on the lathe. I have seen some mills with scraped slides, though obviously that's not a feature on this mill. Surprisingly though, the base where the column mounts to the bed does feature hand scraping, though it really is up in the air to how good that scraping really is. The action on the hand wheel is nice and smooth, and to my surprise, each hand wheel is keyed and each one features a thrust bearing. It's a huge step up from the metal on metal that we got with the lathe. And surprisingly, the hand wheels are made of metal this time round. Furthermore, each axis has a slide lock and tapered gibs, which is a huge improvement over the grub screw locking gibs that we got on the lathe. Overall, it feels like a huge step forward and it feels so much better designed and put together. It's not all perfect though, there are some issues. For one, it still suffers from the paint chipping issue that the lathe suffered from. I suspect that a lack of primer on the cast iron is in part responsible for this. Most of the paint chipping occurs around the spindle lock, though it is found all around the mill. The next issue that I found, and I was very annoyed about it when I discovered it, was rust. I took off the top cover and I discovered a lot of rust. It's the only place I found it, and thankfully it wasn't on a critical surface, but it is very disappointing to see. My final issue is the set screws used to tram in the column. There's a hole either side of the base, and adjusting a set screw will lift one end of the column, tramming it in, but for some reason, instead of tapping the holes, they used threaded taper pins, and unbeknownst to me, the pin must have come loose. I vacuumed it up and didn't notice, hence why the column is trammed in via the use of some razor blades. So let's finally begin the deep dive, and I'll start with the head and spindle. This mill comes with a Morse 3 taper spindle. Coincidentally, that's the same taper as my lathe spindle, and I personally think it's quite useful to have tooling that I can swap interchangeably between the two. For example, swapping in the collet chuck into the lathe. I'm also able to make Morse 3 taper tooling in the lathe and then use it in the mill, knowing that the tool will have next to no run out. You can also get this mill with an R8 taper spindle, but it seems to be mostly reserved for the US market. It seems that for smaller mills in Europe and Australia, Morse 3 taper is the most common spindle taper to find, at least on small mills. Overall, Morse 3 taper is a lot more common here, so that's why I settled on this rather than getting an R8 model imported. However, Morse 3 isn't without its faults. Morse taper is a self-holding taper. It self-holds itself in the spindle by itself, hence why it's very popular with drill presses. My drill press uses a Morse 2 taper. The process for swapping out tooling though is a bit of a hassle. At the top of the spindle we have the M12 drawbar. The drawbar is what critically makes this more than just a glorified drill press. The drawbar threads into the tooling and it prevents the tooling from coming loose. Morse tapers are good when it's subjected to loads pushing it into the spindle, but milling loads pull the tool down and load it from the side, so a drawbar is necessary. If you don't have one, the Morse taper tends to pop out. A good example of this is trying to use a drill press as a mill. Typically the taper will just pop out. Now to remove the tool, you'll need to undo the drawbar, maybe one turn, lock the spindle, and you'll need to give the drawbar a few whacks with a hammer to loosen the tool. Ultimately, this just takes a fair amount of time, whereas R8 doesn't suffer from this issue. You just undo the drawbar and the tool tends to fall out. It's not a criticism of this mill, it's just a fact of the Morse taper design. Quality wise, the spindle is really nicely machined. It's smooth, it has no burrs. I don't have any, but it'll be very interesting to blow up the spindle and see how well it's contacting against the taper. So far I haven't had any issues at all with the bearings. According to the exploded diagram, there are some deep groove and thrust bearings in the assembly, and that's a really welcome sight to see, though in the future I'm planning on swapping them out with some angular contact bearings, but that's a project for another time. Run out under no load is about 10 microns, which is really good. Low run out improves tool life and the quality of the parts that you make. The only thing that I dislike about the spindle is the locking spanner. It uses these two studs to lock in these two holes to lock the spindle in place. The studs are really small and it's very easy to slip out and you can easily cut your arm on the vise or the workpiece. On the right hand side, you'll see a 3-levered hand wheel to drop the quill. As well as moving the head, you also have access to a quill like a drill press. And you have about 70mm of travel, which is a good amount. It's about the same as what I have on my drill press. The quill is mostly used for drilling. It's not hugely rigid, so I prefer to move the head using the hand wheel for milling. As well as the hand wheel, there's a fine adjustment knob. You engage it by tightening this hand wheel, and it's connected to a 30:1 worm gear, so you can make some really fine adjustments. On the front side, we'll see an inbuilt DRO that measures the spindle movement. It's pretty much a digital scale, similar to one that you'd see on a digital caliper. It's powered by an LR44 button battery, and it will probably go about a year before going flat. The DRO is super useful in drilling holes, but I also use it to precisely set the end mill height. Typically, I'll lower the head so the end mill is 2 to 3mm over the work, and I'll do all the fine depth adjustments using the Quill and DRO. Though I don't typically use this for anything more than 20mm of movement, or you really do start to lose rigidity. And I always lock the quill when machining. The movement of the head is done by cranking this hand wheel that connects to a bevel gear. The action is very nice, though every crank of the hand wheel moves the head 1mm. There's a 2:1 reduction in the bevel gears, and as a result, you can spend a lot of time cranking the hand wheel to move the head up and down. And always remember to lock the head once it's in place. And I'll quickly note that the smaller X2 mills don't have a quill or a gear-driven lead screw. The head is moved using a rack and pinion, and you have to move the whole head every time you want to raise and lower the end mill. I've gone and removed the cover from the top of the head. At the back we can see the area where the motor is mounted beneath. At the back we can see the tachometer that reads the RPM of the machine, and the RPM displayed is converted as it's measuring the motor RPM, not the spindle RPM. And it looks like it uses a Hall effect sensor. It reads how many times the magnet passes by. This mill, unsurprisingly, uses a belt-driven spindle. It uses a 5M385 timing belt, and in the event that the belt snaps, a replacement one is only about $15. I only point this out because some of the X2 models have plastic gears instead of timing belts, and on occasion, the teeth have been known to break. Next, let's look at the column. When it comes to smaller mills, there are two types of columns. The smaller X2s usually come with a tilting column. It's a column that's bolted directly to the mill using one huge bolt, and you have the ability to tilt the column to machine parts at an angle. This might seem like a very useful feature, though it's not particularly rigid, and after use, the column has been known to untram itself. The better, more rigid design is a solid column that bolts directly to the bed. That's what's on this model and the X2LF model. You do lose the ability to machine parts at an angle, but the trade-off is worth it. And one final thing, don't be fooled by the cover. The column is only about 80mm wide. The machine, however, is decently rigid by itself, though some extra metal on the column will probably go a long way in improving rigidity. Now there isn't too much to say about the control panel. The E-stop works as the on-off button. Use the toggle to select the spindle direction. Most of the time you'll use setting 2. To make the spindle go, you'll need to go about 1/3 of a turn before anything will happen. One thing to look out for though is every time you start the machine, the fault light will stay on for about 3 seconds before switching off. I wish I'd known about that before I bought the mill, because the first time that I booted it up, it was a very long 3 seconds, thinking that something was already broken before I'd done anything. On the back, there's 2 USB ports, presumably to plug in some work lights. It's a good addition, though I have yet to use them. Finally, let's talk about the table and base. As I mentioned before, the reason why I settled on the 2.7L was the size of the table. It's 700mm long, 100mm longer than the standard model. The table is 160mm wide and 35mm in height. It's a really decent and solid piece of cast iron. The only thing that I really wish I could have more of would be about 30mm extra of Y table movement. With the table fully forward, the spindle is still hanging over the table by about 30mm. It pretty much means that about 30mm of the width of the table is unusable, which is not that good. To clamp vices and work to the bed, you will need to make use of these nicely machined T-slots. The mill lists them as 12mm T-slots, which means they are M10 T-slots. Much easier just to write M10. A good word of warning though, the T-nuts that the mill comes with needs to have the bottom threads punched over using a center punch. If you don't do this, you can easily drive the threaded rod or bolt into the T-slot when you're tightening it. As well as the main 3 T-slots, there's also one that runs down the length of the table that you'll have to make your own T-nuts for. And unlike the main 3, this one here is M5. The front T-slots aren't generally used for fixturing parts. I believe their main use is to clamp table stops in place. Instead of using it for that, I made use of the T-slots to fix my X-axis DRO to the mill. I did it mainly to save me from drilling holes into the back of the table, but it's also much easier to work on the front of the mill than the back. And to keep chips out of the T-slots, I cut some 10mm aluminium extrusions to length and I snapped them into the T-slots. On the front of the table is a metric scale, and take it from me, you'll probably never use it. Next we have the tapered gibs. It's a singular gib design and it's adjusted using a slotted screwdriver. It's a good design, it works well, and it's a huge improvement over the 3 grub screws that the lathe uses. And it looks like I got serial number 00213. This lathe uses 2mm pitch lead screws, so for every turn of the hand wheel, the table will move 2mm. The X-axis lead screw is located under the table and it's relatively easy to oil. To get access to the Y-axis lead screw, you will need to retract the bed and push back the cover. And I use an ISO 68 hydraulic way oil to lubricate the lead screws. Each hand wheel has an adjustable dial. They use the same flat spring design as the lathe, though I don't recommend taking it apart because it's pretty difficult to push it back together. The X-axis hand wheel features a dog clutch. When you want to move the table, you will need to push in the hand wheel, and this can get really tiring because you're pushing against a pretty strong spring the whole time. I recommend reversing the whole sub-assembly to make your life a lot easier when cranking the hand wheel. Overall, it's a really good design, especially for when you have a power table feed. It will prevent the hand wheel from speeding up at 100 RPM, but without one, it's not super useful. Now because you are using lead screws, you'll have to deal with backlash in 2 directions. On a lathe, it's not a big issue because you tend to make a cut in one direction, but on a mill, you're constantly moving backwards and forwards during a single cutting operation. Now the backlash is pretty small in both X and Y, around 0.2 and 0.24mm respectively, but to make accurate cuts, you'll need to account for it every time you change direction. Alternatively, you can install a DRO, which use glass scale linear encoders to read the table's location, and that's displayed on a digital readout. I recommend getting a DRO, even if accounting for backlash is a good skill to pick up. However, if you buy a 4-inch vise like this one, a DRO is a must-have since the mill vise will cover the hand wheel dial. At the other end, we have a button oiler for oiling the lead screw's plain bearing. And like the lead screws, I use an ISO 68 hydraulic oil for doing this. If you ever need to fit the power table feed, this end plate comes off and you bolt the power feed on to this end. The lead screw is slotted so it can mesh with the drive shaft. It's probably a good investment further down the road, however an off-the-shelf model is pretty pricey at about $500. For less than half the cost of a commercial one, I'm sure it's not that difficult to make one yourself. On the back of the table and on the column, there are these accordion style way covers. They do a really good job at keeping chips and debris off the ways. Strangely enough though, all the product photos would suggest that this mill should have a front way cover, though mine for some reason doesn't. I'm not sure why, maybe they just forgot or ran out that day. They're not that expensive and I can always install one in the future. Finally, at the back of the table is a drainage port. If you use enough coolant, it's going to pile up in the teak slots, so a drainage system is pretty useful. The thread is a metric fine pitch M16x1. I made up a small 90-degree elbow insert that screws in and drains to a small bottle, and that's worked just fine. The last thing to do is see how the mill machines. The mill has the most amount of torque between 500 and 800 RPM, so I typically run my end mill at that RPM and adjust feed rates to match the material. And 90% of the cuts are done using conventional milling. It's really easy for climb milling to pull the end mill into the part due to backlash. Now, aluminium is always an easy material. That's a 3-flute 8mm end mill taking 5mm depth of cut at a full width of cut without any issues. And this mill certainly has a lot more to give. Brass is also a pretty easy material. I use a higher RPM for brass and it machines beautifully. Cast iron is also a material that I did some machining with. That's a 2.5mm depth of cut on a 10mm end mill. Ultimately, my fixturing of the part really limited the cuts that I could take in the material, though I was very impressed with what I could get from it. And that's a 20mm finishing cut. The most that I put the mill through is machining the new lathe cross slide. Most of the work was done using a 10mm end mill, taking 1.5mm depth of cut at a full width of cut in some mild steel. I'm sure there was certainly a little bit more that I could get from this part. I wasn't using the highest quality end mill and it wasn't the sharpest, so that was holding me back, but I was pretty happy with the results that I was getting. I'm sure there is a lot more that I can get from the mill, though what is ultimately holding me back at the moment is the limit of rigidity. The areas of the mill that I'll try to improve in the future will probably be the column, the spindle, and how the head mounts to the column. Those are the 3 weak areas. But don't get me wrong, I'm very impressed with the mill, and it's a huge step up from the small CNC router that I was using beforehand. So, was it worth it? I think that's the answer that all of us are here for, and I think that answer is yes. In my opinion, this is the best value import mill on the market. You certainly get more for your money than you would get with a smaller X2 mill, at least out of the box. And if you really need anything bigger, I think it's worth looking at a used mill or one from a name brand. Overall, this mill ticks all the boxes that I was after. It's well made, it's much better designed than I was expecting, and I can make parts to within my general tolerances that I set out. Usually plus or minus 0.05 of a millimeter, though this mill can do slightly better than that if I really need it. Overall, I'm really happy with it and for what it is. One thing you should consider though is how good the used market is for mills in your part of the world. In my part of the world, benchtop mills on the used market are not incredibly common. If you live in North America or parts of Europe, it's going to be more common to find older used equipment, and I think it's a really good idea to consider an old mill over one of these. And of course, if space is limited, this mill can really get a lot of work done in a small amount of space. And that looks to be it. I know this was a bit of a long one. I really hope you found it useful and learned something new. And with that, thank you very much for watching. See you in the next one.